This section is on differentiating natural logs, but we start by integrating dx over x. So we'll write it as x to the negative 1 dx. Try to use the power rule. You get x to the 0 over 0 plus c, but you can't divide by 0. And so the power rule fails in this case. Now what ends up happening is we can define the integral of dx over x to be equal to natural log of absolute value of x plus c. And won't go into too much detail with this, but the idea is that this area accumulation function behaves like its natural log of x in every respect. Now I'll show you here then a graph of what I mean here. And so we have ln x, or graph, and then we'll do function integrate of 1 over x with respect to x from 1 to x. So this is going to graph the integral of 1 over x, starting at 1 going to x, and there's ln x. So first we do ln x, there it is, and then you can see the other function is going exactly along ln x. And so basically it behaves the same way, so that's a very rough showing that these things are equivalent. Okay, now if we can integrate one way, we can differentiate the other. So the idea behind this particular section really is going to be derivative with respect to x of ln absolute value of x, or just ln x, is 1 over x. So we're going to be going this direction. So here's an example. We have y equals ln 5x, so put into this new differentiation rule, which we add on to all the others we've done. It's just one more rule. It's 1 over whatever's inside, so 1 over 5x, times the derivative of 5x, which is 5 by the chain rule, and so you get 1 over x. Now note I can use properties of logs and split this up into ln 5 plus ln x. The log of the product is a sum of two logs. Ln 5 is a constant, so the derivative of that is 0, so 1 over x. So as you can see, the derivative of ln ax, where a is a constant, is just 1 over x. Okay, we always want to try to use properties of logs if we can before we differentiate to make things simpler. So using properties of logs, I can split this up by factoring the inside and put in the radical as a 1/2 on the outside. Take a derivative and the half stays out front. Derivative of x plus 2 is 1 over x plus 2. Derivative of x plus 2 is 1. Plus 1 over x minus 2. And then if there's more than two fractions, I wouldn't bother trying to combine them with just two fractions. We try to get a common denominator. And we have our new numerator. Some things cancel out. And we get all the way to here. If I had not used properties of logs, I would have done 1 over whatever's inside, so 1 over that, times the derivative of this, so that's half x squared minus 4 to the negative 1/2, and the derivative of x squared minus 4 is 2x, and I get the same thing, but in general you want to use the properties of logs first. Now if you don't have a log there already, then sometimes you want to introduce a log to make things easier. Now this is a case where you could use the quotient rule, or you could use chain rules and product rules and power rules, all that stuff. You have to use some of it, but it'd be easier if there were a log on the right. So we introduce that. Put a log on the left, put a log on the right. Now that you've got the log on the right, we can separate the whole thing. So we've got ln x plus 3, ln x minus 3 from the top, and then minus the 1/3 is because it's a cube root, ln x plus 4. So the derivative of ln y is something over y times the derivative of y, so y prime. So it's 1 over y times y prime. And I take a derivative of each one of these. Then you want to get y all by itself, so what you need to do is multiply y to the other side, and y is this big expression here, so you just multiply it over. Now, there's three fractions, that's when I don't bother trying to get a common denominator. So that would be fun. So here's another situation with x to the x. So once again, you have to have a log in here to get this x down, so logarithmic differentiation is necessary. So you take a log of both sides. Ln x to the x, I can take this exponent and put it in front as x ln x. The derivative of ln y is 1 over y times the derivative of y, so times y prime. And then this is going to be product rule. So it is derivative of x, which is, actually we'll do x times the derivative of ln x, which is 1 over x, plus the derivative of x times ln x. That's how we get 1 plus ln x. So it's product rule. And then again, you multiply the y to the other side, and y was x to the x, so here's your answer. A couple more logarithmic differentiation examples. Well, let's get into this one. We have ln x to the x, so I take a natural log of both sides. Then I can put this x in front of the whole thing. You differentiate. You've got to fix it up a little bit. Pause that if you want to spend more time on it. Here's now x to the sine x. Same idea. Ln on both sides, then put the sine in front. This is going to require product rule, and then you multiply the y back.